Okay, so section 2, calculating probabilities using simple events. So a lot of us, this is what we're used to finding. In other words, let's say we wanted to, and I'm just start off with an example here. So let's say you flip a coin and you're asking the question, what is the chance of it landing with the heads of the side of the coin facing up? Okay? So if you think about this, the simple event would be flipping a coin, all right? Your sample space is going to be, and let's say I'll call it F for flip. You have basically two outcomes, heads or tails. And since there's only one head and only one tail, and we're interested in heads facing up, you would say there's a 50% chance, or 0.5. Now, mathematically, what this looks like is the probability of heads is going to equal the number of ways the event occurs. In this case, the event is heads divided by your sample space. So, how many different ways can we get a head on a coin? Well, there's only one way. I have two possible outcomes. So, the probability of obtaining a heads when you flip it is 1 over 2 or 0.5. Now, traditionally, we will use a decimal. All right? So, make sure you are reading the directions on your homework and you're rounding appropriately. Okay? So, please just read the directions, even the parentheses, because it says round to 2 decimal places, around to 4 decimal places, and you will get the problem wrong, even though your answer is right, because you didn't just follow directions. So please, just make sure you read all the directions and not just a little portion of it. So now that we can see probability, we can go ahead and formally define it. P of A equals the number of ways event A occurs divided by the total sample space or total outcomes, whichever one you prefer. Okay? All right. Now, one thing we do need to be aware of, okay, is this what we just have here defined. All right, this is it's an approximation. All right, it's a theoretical thing. Like theoretically, this is what you would get. Okay, now you may be sitting there scratching your head and going, "What is he even talking about here?" Like we just calculated that the probability of getting a heads is 1/2. Okay, well let me show you something here. We're gonna go back here. I'm gonna go to the Google machine. And the reason why I'm coming to the Google machine is because they have this really neat little thing. And it's called a coin flip generator. Oh, sorry, wrong. I clicked on the wrong one. They have their own, and it's very simple. There it is right there. Okay? And as you can see here, it flipped the coin, and notice that it came up heads. So what I'm going to do here is I'm going to create a little table. And I'm just going to keep track. That's it. So flip one, we got heads. And we're going to do this 10 times. Now, if you think about this, if we do this 10 times, we should get exactly 5 heads and exactly 5 tails. Because probability of flipping a coin, you should get 5 heads and 5 tails if you flip it 10 times. But let's see what happens here. So there's first flip. There's our second flip. All right, third. Fourth. Here's our fifth. Oh, here's our sixth. Here's our seventh. Now you can see what's happening here. Oh, geez. Here's 8 flips. Come on, give us a tails. Come on. There it is. There's our 9, and then the last one. All right. So the grand total here, we got 7 heads and 3 tails, which kind of contradicts the it should be equal idea. Here's what's happening, okay? Remember, when we're finding the probability, all right, we're assuming here that the experiment is repeating infinitely. In fact, if you read your book, okay, it basically defines the probability of an event like this. And this is why I'm going over this, because you may never have seen this before. All right, so this is how your book defines it. And it's correct, all right, but I think it's a little confusing. So let me explain what this is saying here. This is saying that the probability of event A occurring, that's right here, is equal to the limits as n goes to infinity. And what that means is, all it means is just to keep repeating the experiment. And how many times are we going to repeat this experiment? An infinite number of times. So if we keep flipping the coin an infinite number of times, we should end up getting a fair split of 50-50, meaning 50 heads and 50 tails. And that's what's happening here. We call this the law of large numbers. Meaning, if you repeat a process over and over and over and over again, and you're calculating probabilities, all right, you will start to converge to the true theoretical probability. And we know that, on a coin, there are only 2 sides. There's heads and there's tails. So every time we flip, we have a 50% chance, or 0.5, of getting heads. Okay? But notice, if I repeat the experiment, it starts to change a little bit. Okay? However, according to this law of large numbers, according to the law of large numbers, I should get 50% heads and 50% tails the more I repeat this process. So I'm going to go back, because I think I might have seen this. I can't remember. But let's go to Blackboard real quick. We're going to go back into SALT real fast. Where is your class? It's right here. I have way too many classes. All right, so here's SALT. All right, and I think, is it sampling? No. Info. Distribution calculators. Is that it? No, I thought I seen like a coin flip thing, like a coin flip simulator. Excuse me, inside SALT. Maybe I didn't. I don't think I did. I think I'm losing my mind. But that's okay. We'll get back on to what we're doing right here, because the coin flip simulator would just allow me to flip, it would allow me to flip 50,000 coins in a second. All right. Properties. All right, now this is properties for probabilities. So properties for P of A. First, each probability. So each probability that you calculate is going to be in between 0 and 1 inclusively. meaning you include 0 and you include 1. If your probability is 0, your event will not happen. If your probability is 1, your event is certain to happen. Okay? So if you think about it, if you are holding a ball at chest height and you drop it, it will hit the ground. Gravity says so. So that is a probability of 1. If you were to hold a ball chest height and you were expecting it not to fall, that would be, that obviously that is not going to happen, because it's definitely going to happen. So you might think of that as probability of 0. Maybe that's a bad example here. But think of another one. It's not. Okay. In the middle of August, it's not going to snow in the United States. It's just, we're in summertime. It's never snowed once in August, ever. So that's a probability of 0. Okay. The second property is that the summation of all of your properties has to total up to 1. Now, let me show you what I mean by that, okay? In the previous video, we looked at rolling 1 die. And we found our sample space to be 1, 2, 3, 4, 5, 6. And what I'm interested in is the probability of rolling a 4. Well, if you think about it, how many different ways can I roll a 4? Well, there's only 1. And there are 6 possible outcomes. So this is going to be the probability of 1 divided by 6, or approximately 0.167, okay? And that's just rounded. So we're going to leave it like this. We're going to leave it as 1/6. I like 1/6 because I'm driving home a point here, all right? Come on, pen work. Here we go. Now, if I wanted to roll a 1, once again, that's 1/6. And to be honest with you, it is 1/6 for every single possible event. So if you take 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6, you are going to get 6/6, which is equal to 1. And that's what we mean by the summation of all the probabilities have to add up to equal 1. Okay? Excuse me. Now, I can ask the same question, or better yet, let me ask you a different question. How about this? What do you think the probability of rolling at least a 4 is? Take a second and think about it. You want to roll at least a 4. So when we think about that, you can roll a 4. You can roll a 5. You can even roll a 6, because remember, the question is saying at least a 4, which means 4, 5, or 6. So the probability of rolling a 4 is 1/6. The probability of rolling a 5 is 1/6. The probability of rolling a 6 is 1/6. And if you add all those together, you get 3/6 or 1/2. So make sure that when you're reading these questions, you're taking your time. At least means you are including that number and you want more than that. At most, let's look at another one here. What's the probability of rolling at most a 2? Well, at most means a 1 or a 2. Okay? Because you want at most 2. You don't want anything else. So this is going to be 1/6 plus 1/6, which is 2/6, or 1/3. Okay? All right. So I hope this is making sense. We're just talking about probabilities with simple events. Okay? All right. So let's look at this example here. This example, we're going to kind of step it up a little bit. So we have a sample space consists of 5 simple events. All right. And we're going to call these events E1, E2, all the way up to E5, okay? So E1, E2, E3, E4, E5, all right? And I'm going to also give you the probabilities of these. So the probability of event 1 equals the probability of event 2, and they equal 0.25. The probability of event 3 occurring equals 0.2, and then the probability of event 4 is equal to 2 times the probability of event 5, okay? Our goal right now is to find the probabilities for event 4 and event 5. So if you think about this, we kind of meet the criteria. Notice that all of my probabilities that I know of right now, probability of event 1 and 2 equals 0.25, probability of event 3 equals 0.2. They're all between 0 and 1. And I know if I were to add all of these up, it has to equal 1. Okay? So we're going to use that to our advantage. In other words, here's what we know. Probability of event 1 plus event 2 plus the probability of event 3 plus the probability of event 4 plus the probability of event 5 has to total up to 1. Now, we're given the fact that events 1 and 2 is 0.25 and event 3 would be 0.2. So I'm going to write that directly underneath. So 0.25 plus 0.25 plus 0.2, okay? Excuse me. What we don't know are probability of event 4 plus the probability of event 5. So if I were to total these up, I would get 0.25 plus 0.25 plus 0.2, which is 0.7 plus the probability of event 4 plus the probability of event 5, and that has to equal 1. From here, I can subtract 0.7 from both sides of my equation, and that leaves me with the two unknowns that when I total event 4 plus the probability of event 5, those two probabilities have to equal 0.3 because 1 minus 0.07 is 0.3. From here, we definitely know something about the equation that we have left over. And here's what it is right here. I'm going to highlight it for us. We know that the probability of event 4 is equal to 2 times the probability of event 5. So what I'm going to do is instead of writing the probability of event 4 again, I'm going to write 2 times the probability of event 5 plus the probability of event 5 has to equal 0.3. Okay, because that is just a direct substitution, which means we have 3 times the probability of event 5 has to equal 0.3. And then if I just divide both sides by 3, I found that the probability of event 5 is equal to 0.1. And since we know, I'm going to zoom out here a little bit so you can see them in the upper left-hand corner. Since we now know what the probability of event 5 is, we can find the probability of event 4. I'll just write it over here to the left-hand side. Probability of event 4 has to equal 2 times 0.1, and 2 times 0.1 equals 0.2. So I guess all the way at the end of this, we can just kind of summarize everything. Okay. Probability of event 1 equals the probability of event 2. And we know they equal 0.25. Probability of event 3 equals 0.2. Those were given. Now, probability of event 4, we just found 0.2. And the probability of event 5 is 0.1. And just to check yourself, remember, I'm going to go back to my black marker now. If you wanted to check yourself, all you have to do is just write them all out. And just add them up. 0.25 plus 0.25 plus 0.2 plus 0.2 plus 0.1. And if you do the math, it does check out. Everything adds up to 1, which is exactly what we would expect. All right, the last problem that I want to go over deals with what we call a probability table. Okay? So, probability table. All right? And that'll look something like this. So, I'm going to just basically do a problem that's very similar to your homework. So, we have a basketball player hits 70% of their free throws. All right? Sorry, I'm writing way too fast. When they toss a pair of free throws, the 4 possible simple events and their probabilities are listed below. So here's what a probability table actually looks like, okay? You just have a big box. This is going to be our first free throw. And you either hit it or miss it. Now, over on the left-hand side, we're going to have our second shot. And that you either hit it or miss it. And here are the associated probabilities. Okay, so if you just take a second real quick and just look, if you make your first free throw, I can't even say it. If you make your first free throw and your second, I'm not even going to say free throw anymore. I'm just going to say shot. All right, so much easier. If you make your first shot and your second shot, the probability of that happening is 0.49. If you miss your first shot, but then you make your second shot, that's a probability of 0.21. If you make the first one and you miss, the second one, we don't know what that probability is, so it looks like we're going to have to find that. All right. And then lastly, if you miss the first and you miss the second, probability of that happening is 0.09. So that is not likely to happen. Okay? So what we want to do first is let's find the probability that the player will make the first and miss the second. So find the probability of making the first shot and missing the second shot, okay? The second thing we're going to want to do is we're going to find the probability that the player will hit at least one of the two free throws or shots. So probability of making at least one of the two shots. Okay? So, part A first. Excuse me. Well, if you think about probabilities and their properties, we know that all probabilities have to be in between 0 and 1, and when you total them up, it has to equal 1. Therefore, if I think about each one of these as like event 1, event 2, event 3, and event 4, then here's what we know. All the events, when I total them together, so all the probabilities, let me get a better marker. Here we go. So all the probabilities have to total up to 1. So if I know 3 out of the 4, I can easily find the missing one. So all we're going to do is just substitute and then simplify. So event 1 is 0.49 plus 0.21 plus, well, I don't know the probability of event 3, so we'll leave it. Probability of event 4 is going to be 0.9. And that has to equal 1. So when I add all of them up, let's see here. I'm going to get my trusty calculator out. 0.49 plus 0.21 plus 0.09 is going to be probability of event 3 plus 0.79 equals 1, which means the probability of event 3 is going to equal 1 minus 0.79, or 1 minus 0.79, 0.21. So we can go back up into our table now, erase the question mark, and put 0.21. Okay, so now for the second question. We want to find the probability of making at least one of the two shots. Okay, so we want to find the probability of making at least one of the two. All right, so part B. I'm just going to rewrite it. I was going to copy and paste it, but it's going to be too much. Okay, so we know what our table is, okay, and we know all the values. So actually, you know what? I'm going to copy and paste our table because I don't want to have to keep scrolling up and down and everything. All right, so let me copy and paste this. Copy and paste. There we go. Beautiful. All right. So when we think about this, all right, we have 4 events. We have the situation where this person hits both of the free throws, both shots, or they have the situation where they make the first, miss the second, or they miss the first and make the second. So when you think about at least one, that's going to equal the probability of event 1 plus the probability of event 2 plus the probability of event 3. Because remember, event 1, you hit both. Event 2, you miss the first and you hit the second. Event 3 is you hit the first and you miss the second. And the problem is just asking us, what's the probability of making at least one of them? So that's one or both, okay? So now that we know that, all we have to do is just use our table and write down the associated probability. So the probability of hitting both, 0.49, plus missing the first and hitting the second, 0.21, plus hitting the first and missing the second, 0.21. And when you add all these up, the probability of making at least one shot, 0.91. So although the problem may have looked a little confusing, it's actually very easy. It's just, you just got to take your time and think about what the problem is asking. I'm going to leave you with a little piece of advice. And this is please don't play the what if game. All right? And what I mean by that is this. The what if game is like if I say you were flipping two coins in the air at the same time, you want to find a probability that they both land on heads. Don't play the what if game, which is, well, what if the coins hit each other in midair? Well, I didn't say it did. So whatever the problem says, that's what you have to stick with, okay? A lot of times we play the what if game, and what ends up happening is we lose sight of what the problem is really asking. Another example of the what if game is you are setting up 5 alarm clocks because you got a really important job interview, and you live in 1980 and you do not have a cell phone, which means you're using the old school alarm clocks that plug into the wall. What's the probability that at least one of them fails, okay? And then I always have like one student that goes, well, what if the power goes out? Then they all fail. Well, the power doesn't go out. I didn't say it went out in the problem. So try not to play the what if game. Just stay focused on what the question is asking. And if you can do that, and if you can remember, and I'm going to scroll all the way back up. If you can just remember this definition that's at the top of your page, the probability of event A occurring is equal to the number of ways that A can occur divided by the total sample space, you're going to be fine. So good luck. I'll talk to you next week.